Look to the future with BBC Learning Zone in 30 minutes, to a time when people have merged with technology to overcome the limitations of the human body. It sounds like science fiction, but the age of cyber souls could be closer than you think. That's after the OU shows how velocity diagrams can provide engineers with a speedy solution. This programme was made before the current legislation on health and safety had been passed.
Suppose two cars are approaching this crossroads. One car, the red car, is travelling at 30 miles an hour, 13.5 metres per second. The second, blue car, is approaching along the road at a constant speed of 40 miles per hour, 19 metres per second. How can we tell if they're going to collide? If we fix the coordinates relative to the ground, it's hard to tell. Is there a way of representing their velocities so that we can get this information? Suppose we were to fly along exactly over the red car. In other words, we fix our axes relative to the red car. We then only have to watch the blue car for as long as it takes to measure its position and its velocity. On this enlarged picture, we can see the red car on the left and the blue car at the top. Let's run that again and add a set of axes. We can see from this relative velocity diagram that the blue car is heading straight for the red car. Without the need for any calculations, we can deduce the result by choosing the correct axes. This procedure can also be used to analyse engineering mechanisms.
Well, remember the engine you saw in an earlier programme? We've shown the slide crank mechanism in operation, and we've slowed down the line diagram so that you can follow the motion of each individual link. But even so, it's still difficult to see the motion of all the links at one moment. So, how do we capture the total picture of all the velocities of all the points on the piston, the crank and the connecting rod all at once? Well, to find out, we have to freeze the motion, such as at this instant of the cycle.
The picture of all the velocities at a given instant is, of course, the velocity diagram. Now, I'm going to go briefly through the construction of a velocity diagram for a slider crank mechanism. The first thing we have to do is to label the diagram. I'll call this fixed point O and the other end of the crank B. The slider is C. And of course, wherever there is a slider, we also need a coincident point. I'll call that D. It's important to note that this coincident point, D, is only appropriate for this particular instant. The position I'm actually going to analyse is this one. So the coincident point must be here. Right, now the position diagram is complete, I can start on the velocity analysis. The first thing I want are the fixed points. And these are O, and of course also the coincident point on the frame here, D. The input information is for the crank OB, so OB is the link with input data. Now the next step in the starting procedure for this sort of problem is to find the basic chain. And you remember that the basic chain must be a 4-link chain which includes the input data. Well, in this case, it's just OBCD, and there are no appendages. So now I can start drawing the velocity diagram. The first thing I want to do is to mark on the fixed points. And these are O and D. The first moving point that I'll be able to plot is the point B. Now, the velocity of B relative to O, well, OB is rotating anti-clockwise, so velocity of B will be in that direction. And its magnitude, well, that's just given by omega r. So velocity of B relative to O is 2 times 40 is 80 millimeters per second, and it's in that direction. Now, to mark that on the velocity diagram, I want to draw a line through O perpendicular to the link OB. And to do that, I'll set my ruler up and use the square. And I know that B must be somewhere down that line. Now, at the scale we're using for this diagram, I just have to measure 80 millimeters, and that will give me the point B. And this length represents 80 millimeters per second. Now, what about the motion of C? Well, C slides vertically relative to D. So in the velocity diagram, there's D. C must be on a line vertically. So I can just extend the existing axes, and that's a C line. What about the motion of C relative to B? Well, they're both on a rigid link, so velocity of C relative to B must be perpendicular to the link BC. So I'll set my ruler along BC and use the square to get the perpendicular. If I draw a line through little b, then C must lie on it. Well, now C lies on both of these two lines, and therefore, of course, that must be C there. And now I can measure off the lengths and see what actual velocities they represent. And that one is 43 millimeters per second. And this length represents 60 millimeters per second. Well, that's the complete velocity diagram, but what does it actually tell us? How do we interpret the diagram?
Well, what the velocity diagram tells us depends entirely on one's viewpoint, because the velocity diagram is really about relative velocities. So, if I stand here at O, then John's velocity diagram tells me that I'll see B moving in that direction with a velocity of 80 millimeters per second. And I'll see C coming downwards onto me with a velocity of 60 millimeters per second. But if I happen to be part of B, then I would see O moving that way with a velocity of 80 millimeters per second. And I would observe C moving in that direction with a velocity of 43 millimeters per second. And of course, if I were to be part of C, then I would see a completely different picture of the velocities. So the idea of a velocity has no meaning unless it is specifically related to a point of reference. In that way, all velocities are relative velocities. How I see the motion of other points around me will depend upon my own motion.
Well, this velocity diagram that I've drawn only applies to one instant of the whole cycle. To find the velocities in the mechanism throughout the full range of its motion would require a large number of such diagrams to be drawn. And it really used to be done that way, by hand. Well, nowadays we've got computers to help us to do that. This is the position diagram for the mechanism that I drew earlier. The fixed points are those on the frame, that's O, and also the coincident point for this instant, D. There's the velocity diagram for that instant. The velocity of C relative to D is downwards. At this instant, the lowest position, it's 0, and then it's upwards. And then again, it's 0 as the slider changes direction in the topmost position. and then it's downwards again on the downstroke. So throughout the cycle, the velocities change with position. The principles involved in the construction of a velocity diagram for a particular mechanism don't depend on its position. So in the text, you're only asked to analyse one position for each mechanism. Well, why are we interested in velocity diagrams in the first place? Because they tell us all the relative velocities. In an example that we've been considering so far, the internal combustion engine, the velocities are of interest for a number of reasons, including, for example, lubrication. In the rest of the programme, we're going to look at a device in which the velocity behaviour is a central feature of its design. The device I'm referring to is the shaping machine.
The function of a shaping machine such as this is to cut flat surfaces and grooves in metal such as cast iron or mild steel as we have here. A typical product is this table on which the vise is attached. Consider the motion of the tool. It has a constant velocity forwards and a quick return stroke. The constant velocity forward is needed to give a good uniform cut. And the quick return, it saves time. How does a machine like this produce this translational motion with the quick return action from a given rotational constant speed input? Well, you've already seen a quick return mechanism in the text. Have a look at this. It's a quick return mechanism of the type you've already dealt with. The constrained slider is C. The input is to the crank OB, and B slides on the link ED. Notice the constrained slider's quick return motion for the constant rotation of the input link. That mechanism produced a translational quick return output for a constant rotational input, as indeed does this shaping machine here. But this machine does it with a slightly different linkage system. At a first glance, the difference between this and what we had before isn't that easy to spot. The output is exactly the same, a quick return constrained slider, and the input is also the same. This sliding link is also common to both systems. It's at the ends of the large upright link that the mechanisms differ. The machine has a trunnion or oscillating cylinder at the bottom end. That's an inversion of a slider crank. Now compare the machine's linkage with the model we had earlier. The left-hand line diagram is for the machine. Remember, on the machine, D is a trunnion, while on the other link, D is a fixed point. The input is the same for both linkages. Now, if D were a fixed point on the left-hand linkage, the system would just cease solid. It's no longer a mechanism. An extra link at the top slider will give back that degree of freedom to allow the system to become a mechanism again. Now you've seen two systems that produce a quick return motion. In this shaper, the designer chose a trunnion at the bottom, which eliminates the need for an extra link at the top.
Well, here they are in kit form. This one is of the type you've already met in the text. And this one is a model of the shaping machine you've seen in the film. And the purpose of them both is to drive a sliding link backwards and forwards along a straight line. Now, in this case, this long link is pivoted at the bottom. This means that the top of the link will move in a circular arc, so we need a coupler to straighten out the arc, as it were, to give the required rectilinear motion. Now, this long link is effectively changing its length by sliding in and out at the bottom at this guide or trunnion. This means that at the top of the link you have the freedom to move in a straight line. Well, you've already analysed a mechanism of this type in the text already. So we're going to concentrate here on this mechanism. And we're going to get the computer to draw the complete cycle for the velocity diagrams.
Just a minute, one thing at a time. Let's look at one instantaneous velocity diagram for this mechanism first. This is the position diagram. I'll need to label it. I'll call the centre of the driving crank here O, and the other end B. This pivot up here I shall call C. Now, this is a slider sliding horizontally on the frame, so I'll need a coincident point. I'll call that G. Now, this slider slides on the long link. I'll need another coincident point here. I'll call that E. And down here at the bottom, in the centre of the trunnion, I'll need a point on the ground. I'll call that F. And I'll also need a coincident point on the long link. I'll call that D. So now, just to make sure that notation is quite clear, I'll draw a separate picture of the long link. So the long link is C, E, D. Now let's have a look at the velocity diagram. Well, the first thing I want to do is to mark the fixed points, and those are O, F and G. They're all there. The next point I can mark is the moving end of the driving crank, that's B. Now, the velocity of B relative to O, well, OB is rotating clockwise, so VBO is going to be in that direction, and its magnitude is going to be given just by omega r. So, the velocity of B relative to O equals 2 times 0.1, that's 0.2 meters per second, and it's in that direction, perpendicular to OB. And to construct that in the diagram, I'll put my ruler along OB and use my set square, and there's my line. So B's somewhere up there, and at the scale chosen for this velocity diagram, I need to mark off 0.2 meters. So that's little b up there. Now, what other points can I mark? Well, C slides horizontally relative to G, and there's little g, so C must be somewhere along this line here, so this is a C line here. This slider, E slides relative to B, and it slides parallel to the long link. So I want to draw a line through little b parallel to that long link, and to do that I set the set square here along the link, and use the ruler to keep it parallel. I can draw through B to get an E line. E is somewhere along there. Now this bottom slider, well, F is a ground point, and D slides relative to F, again parallel to the long link. So I require the same construction. And this time I want to draw through little f to get a D line. Well, so far so good. Now, what else do we know that would enable us to complete this velocity diagram? Well, CED is a rigid link, so it must have a velocity image. This must be at 90 degrees to the link and have the same proportions. Now D must be somewhere on the D line, and E must be somewhere on the E line. When C is on the C line, that must be the true velocity image. So now I've got the complete velocity diagram. Now the velocity I was particularly interested in was the velocity of the cutting tool relative to the frame. That's the velocity of C relative to O. And now I can measure that straight off the diagram. So measuring from O to C, I get 0.21 meters per second to the right.
Well, again, that was just for one single instant in the cycle. Now we'll get the computer to produce the complete cycle for us. This is the velocity diagram for the instant we've just considered. Of course, the velocity diagram changes as the mechanism changes position. You'll notice that when little c on the velocity diagram is to the left of O, the slider is moving backwards on its return stroke. And when little c is to the right of O, the slider is moving forwards. Notice that the return velocity, when little c is on the left, is considerably larger than the forward velocity when little c is on the right. And this is what you'd expect from a quick return shaping tool. Well, so far in the course, you've looked at two ways of presenting information about the motion of objects. On the one hand, you can draw the velocity time curve for a single point. That's the sort of information you get when you follow the motion of one individual object. And on the other hand, you can draw the velocity diagram for an assembly of points. And that's the sort of information you get when you freeze the motion, to give a total picture of the velocities of all the parts of a mechanism at one instant. Well, we've drawn the velocity diagrams for a slider crank mechanism and a quick return mechanism at one instant. And we got the computer to complete the cycles for us. And that's what it's really all about, analyzing one moment in a complex motion.